In this video, we're going to talk about another practical hands-on issue of how to get gradient descent to work well. In particular, we're going to talk about how to choose the learning rate alpha for gradient descent. And in this discussion, we'll also talk a bit about debugging and how to make sure that gradient descent is working properly. You've seen the formula for gradient descent a number of times already. Just to write it down again, gradient descent updates theta using this formula, and you do this for every value of j. And one of the parameters of gradient descent is this alpha, which is the learning rate. So it turns out that, well, one thing we'd like to do is make sure that gradient descent is working properly. And in particular, gradient descent is trying to find the value of theta that minimizes j of theta. So for the purpose of, let's say, debugging, one thing that's very useful to look at is to plot the value of j of theta, that's the vertical axis, as a function of the number of iterations. And if gradient descent is running properly, what you should get is a plot that maybe looks like that. And let's put some values on the horizontal axis. It says 100 iterations, 200 iterations, 300 iterations, 400 iterations. And it turns out that if gradient descent is working properly, you should be able to see that j of theta decreases on every single iteration. Okay? In particular, if it looks like that and sometimes goes up, sometimes goes down, then something's wrong, and this is not what this plot is supposed to look like. And I just want to make clear, right? We've seen a lot of plots of j of theta, and so just be clear, right? The vertical axis of this plot is the value of j of theta, and the horizontal axis of this plot is the number of iterations. So you started off with some value of theta that gave you some value of j of theta at the start, and then as the algorithm runs, you're slowly changing the parameters theta, and as you change theta, j of theta hopefully goes down, and that's how I get this green line. In particular, the horizontal axis is the number of iterations. So as you move to the right, you get hopefully better and better values of theta. And the horizontal axis in particular is not theta, right? This is not a plot of j of theta as a function of theta. This is a plot of j of theta as a function of the number of iterations of gradient descent. Because as you run gradient descent, theta changes, and therefore j of theta hopefully goes down over time. So let's see. This plot is a good, it's called a debugging or a sanity check plot, and it helps you, verify that gradient descent is running properly. Another use of this plot is it helps you to tell if gradient descent has converged. And in particular, looking at this plot, seems like, curve has mostly plateaued out, or has mostly flattened out around 300 iterations. So maybe by 300, 400 iterations, looks like this curve is flattened out and it isn't going down that much more either. So by looking at a curve like this, you can sort of tell, or help again verify, if gradient descent is converging. I should warn you, I should say, these numbers 300 and 400 were examples that I made up for this for this video. It turns out that the number of iterations that gradient descent takes to converge is very problem dependent. So here we see it's converged maybe by 400 iterations. For a different problem, you may need to run gradient descent for 4,000 or 40,000 or 400,000 or many more iterations. So the number of iterations that gradient descent needs is extremely problem dependent. So it can be any of a huge range of values. And finally, it turns out also that you can come up with an automatic convergence test, right? In which you can look at how much j of theta changes between two iterations, and maybe if j of theta changes only a little bit on two iterations, you can have an automatic convergence test to declare gradient descent as converged. So you can the goal of a convergence test is to decide when you can start doing this, right? Because gradient descent repeatedly does this, until convergence, right? So you can use this sort of intuition to derive an automatic convergence test to see when JF theta is very slowly going down or isn't going down much. Although in practice, I would recommend just looking at this plot visually and just plot this and look at it just to make sure that things are going okay. Now, what if you plot this figure? What if you plot JF theta as a function of the number of iterations, and you get a curve that looks like that instead, right? What does this mean? If you get a curve like that, this means that gradient descent is not working. And there are a couple possibilities. One is that you may have a bug in your implementation, and that could lead to something like that. Another possibility is if you are using a learning rate that is too large. And if alpha is too large, you can also get things like that. And in particular, if this is JF theta, notice the horizontal axis. Now the horizontal axis is theta. So if this is JF theta, this is a function of JF theta, plotted as a function of theta. If the learning rate is too large, then even if you start fairly near the local minimum, one iteration may overshoot, right? Instead of jumping here, overshoot, and then the next iteration can overshoot even more, and overshoot even more, so that instead of starting somewhere and going downhill like we would like gradient descent to do, it can instead end up with this sort of growing oscillation that's causing JF theta to blow up. And so using a learning rate that's too big can cause JF theta blowing up. And it turns out that if your learning rate is too large, depending on what problem you have, you get different phenomena for different models. It turns out that you can also get phenomena like JF theta going down for a while, and then maybe jumping back up, and going down for a while, jumping back up, going down for a while, jumping back up, and so on. And this could also be caused maybe by a bug in the implementation, maybe by using a learning rate that's too large. And it turns out that for a very small alpha, for a sufficiently small learning rate, right, you should have that JF theta should go down let's just write decrease or stay the same on every iteration. And so if you set alpha to be smaller and smaller and smaller, and if this doesn't happen, then you may have a bug in the implementation. And finally, why not use a very small alpha then? Why not use a very small learning rate? Well, the reason we don't use a tiny learning rate is because if this is JF theta with theta on the horizontal axis, if your learning rate is too small, then starting somewhere, you end up taking baby steps. You end up taking such tiny steps that you end up requiring a lot of steps. And so if the learning rate is too small, gradient descent will be slow. Whereas if the learning rate is too large, then you end up with divergence or gradient descent failing to converge. Hopefully that makes sense, why we don't want the learning rate to be too small or too large. I now have a question for you to see if we understand these phenomena. Suppose you have, suppose three of your friends try running gradient descent, and one runs it with alpha equals 0.01, one of your friends runs it with alpha equals 0.1, and one runs it with alpha equals 1. And suppose all three of your friends plot JF theta as a function of the number of iterations. And suppose your first friend, comes away with this plot, and your second friend ends up with this plot, and your third friend ends up with a plot like that. Okay? So my question is, of these figures A, B, and C, which of these figures most likely corresponds to each of these three learning rates? So hopefully you got that this second answer most likely corresponds to maps the figures to the three different learning rates. And let's see. So the first figure, this is a rapidly decreasing cost function that rapidly drops down and then plateaus out, and so maybe that corresponds to a like a reasonable in this example it looks like we corresponds to a good choice of a learning rate. This figure here, right, j of theta is decreasing much more slowly, and so that corresponds probably to a smaller learning rate. And on the figure on the right, looks like j of theta is diverging, and that corresponds maybe to a learning rate that is a little bit too large. Okay, like alpha equals 1. By the way, I should say, it turns out that this is consistent with the picture I've been painting. It turns out that, in practice, it's not as clear-cut. It turns out that if alpha is a little bit too large, it can also slow down convergence. But in this example, here if alpha equals 1, that's like 10x too large, and that's often far too large. It turns out that if alpha is a little too large, you can still converge, but just get slow convergence. But if alpha is far too large, then that's more unlikely to produce reasonable results, and so you're more likely, if alpha is much too large, to get gradient descent to fail to converge at all. Finally, I want to talk about how you would go about setting the gradient learning rate parameter alpha. So, now we know what happens if alpha is too small, alpha is too large, and so on. And so in order to choose a learning rate alpha, one thing I often do is pick a range of values of alpha to search on an exponential scale. So I try, alpha equals 0.001. I might then try alpha equals 0.01, a factor of 10 larger. I might try alpha equals 0.1, alpha equals 1, and so on. And even values smaller and larger than these, right? So you can even go smaller than this, go smaller than these, but this would be searching values of alpha at multiples of 10. So try a bunch of different values, then pick the value that seems to get j of theta to decrease the fastest. Okay? And so this would be if I search at multiples of 10, it could work. What I actually do most of the time is actually search in multiples of approximately 3. So let me add a few more numbers here. 0.3 and so on. And so each step up, that's approximately a multiple of 3, right? So 0.001 times 3 is 0.003. 0.03 times 3 is not exactly, but it's approximately 0.01 and so on. So each step up. So this would be a searching, roughly multiples of 3 to try to find a good learning rate. Or you can search in multiples of 2 and so on. But this is the method that I often use to try to find a good learning rate. Hopefully you now know have intuitions about what happens if the learning rate is either too small or too large. And remember also that when implementing gradient descent, it's good practice to plot j of theta as a function of the number of iterations and verify that it's always decreasing on every single iteration. And this will both help you figure out if the learning rate is too small, too large, or maybe just right, and also help you verify that gradient descent is running correctly. And using these methods, I hope you'll be able to get gradient descent to run well on your linear regression model.